Look around you. Our world is saturated in a light that, for most of modern history, was considered physically impossible. This is the story of one color, a single wavelength that nearly stalled the entire digital revolution. It's a color so fundamental, yet so elusive, that conquering it required defying the world's top scientists. For decades, engineers had mastered coaxing light from electronics. They could make red LEDs, the familiar glow of a standby button. They perfected green LEDs, and even yellow ones. These were the building blocks of a new age of efficient lighting. But there was a gaping hole in the spectrum, a frustrating void that prevented the next great leap forward. A crucial piece of the puzzle was missing. That missing color was blue. For reasons that baffled researchers, that one high-energy wavelength refused to shine. The materials were unstable, the physics were punishing, and every attempt ended in failure. The challenge became so legendary that scientists dubbed the quest for a blue LED the holy grail of optoelectronics. It wasn't just an engineering problem, many saw it as a fundamental barrier drawn by the laws of physics. And without blue, our modern world couldn't exist as we know it. You can't create pure, efficient white LED light, because white light is made by combining red, green, and blue. That means no energy-saving light bulbs that last for decades. More importantly, you couldn't build the vibrant, high-resolution screens that have become extensions of our lives. Every pixel on your phone, your laptop, your television, relies on that once impossible blue to generate millions of colors. The solution wasn't a single eureka moment. It was a saga of obsession spanning 30 years, built on relentless frustration. It involved dangerous high-pressure experiments that pushed the boundaries of safety. It's the story of a few stubborn outsiders who chased a gamble the scientific community had dismissed as a fool's errand. And even after the light finally shone, the story exploded into a bitter billion-dollar controversy over patents and recognition, a fight that went from the lab to the courtroom and all the way to the Nobel Prize. This is the story of the impossible light that illuminates our lives. By the end, you will never look at the screen you're watching on in the same way again. The first LEDs appeared in the 1960s. They worked by taking a semiconductor and making electrons jump across an energy gap, releasing photons. The size of that gap determines the color. Small gaps make infrared, bigger ones make red, then orange, then green. Red LEDs? Done by the mid-60s. Green and yellow? By the 70s. But the problem was that blue light needs a much larger energy gap, and no existing materials could handle it. To make blue light, you need a semiconductor with a wide band gap, more than 2.6 electron volts. Materials like gallium arsenide or silicon just couldn't do it. Scientists looked at gallium nitride, GaN, but it was notoriously unstable, difficult to grow into crystals, and littered with defects. Basically, GaN was the nightmare child of semiconductors. Everyone agreed, blue LEDs were impossible, at least with 20th century tech. By the 1980s, the official verdict was in. Gallium nitride was a dead end. The material was too unstable, its crystal structure too riddled with defects. It was a chemical nightmare. The world's top corporate and university labs had published their findings, declared the problem intractable, and moved on to chase easier, more fundable projects. The consensus was clear, a blue LED from GaN was impossible. But in the quiet corners of the scientific world, a few stubborn outsiders refused to accept defeat. In a laboratory at Nagoya University, Professor Isamu Akasaki and his doctoral student Hiroshi Amano began a quest that many considered academic suicide. Their goal was deceptively simple: grow a perfect single crystal of gallium nitride. For years they toiled. Every attempt resulted in a cracked, useless mess. We're not talking about a few dozen failed experiments, we're talking about over 1,000. Imagine the scene: late nights under the flickering lights, another wafer pulled from the furnace, another microscopic inspection revealing the same fatal flaws. Their funding was constantly under threat. Colleagues whispered that Akasaki was wasting his reputation and that Amano was sacrificing his entire future on a fool's errand. At the very same time, hundreds of miles away, another rebellion was brewing. This one wasn't in a prestigious university, but inside a small, obscure chemical company called Nichia. The rebel was an engineer named Shuji Nakamura. He was not a celebrated academic, he was a company man, but one with a dangerous obsession. He saw GaN's potential with a clarity that bordered on mania. His superiors, however, saw only a black hole for time and money. They explicitly ordered him to abandon the project. But Nakamura was defiant. He famously ignored his bosses, building his own equipment from scratch, modifying reactors in secret, and working with a singular, relentless focus. He was a lone wolf, convinced he could tame the beast that had defeated the world's best. These two teams, the academics and the industrial engineer, were the outsiders, the heretics, the ones who refused to quit. They weren't just solving a technical problem, they were challenging a deeply entrenched dogma. Year after year they pushed on, enduring failure after failure, solving infinitesimal pieces of an impossibly complex puzzle. They didn't know it yet, but their combined, unwavering persistence was about to crack the code and finally unleash the brilliant blue light the world had been waiting for. The breakthrough came when Akasaki and Amano figured out how to grow GN crystals on a sapphire substrate and add a critical layer of aluminum nitride to reduce defects. Later, Nakamura developed a method to create P-type GaN, the missing ingredient for making a working LED. By the early 1990s, for the first time in history, bright blue LEDs were glowing in labs. It was a revolution in a single photon. With red, green, and now blue, you could finally make white light by combining all three. That meant LED lighting could replace inefficient incandescent bulbs, saving massive amounts of global energy. It also unlocked full-color LED screens, high-definition displays, Blu-ray technology, and the backlighting in every smartphone, tablet, and laptop. Without blue LEDs, modern digital life would look very, very different. In 2014, the Nobel Prize in Physics was awarded to Akasaki, Amano, and Nakamura for inventing the blue LED, a technology the Nobel Committee said brought great benefit to humankind. But the story wasn't without controversy. Nakamura had once sued Nietzsche, his former employer, for underpaying him despite his crucial role. He eventually received a massive settlement, sparking debate about how innovation should be rewarded. Take a moment and look around you. That blinking light on your smart speaker, the crisp illumination from your desk lamp, the vibrant colors on the very screen you're watching this on. All of it exists because of one, once impossible color, blue. Its creation was one of the most grueling battles in materials science. But when that first blue light finally shone, it illuminated the future. This single breakthrough gave us white LEDs, slashing global electricity consumption. It made our high-definition screens possible and even saves lives through UV water purification. The story is a powerful reminder that the line between impossible and inevitable is simply persistence. It begs the question, what is the blue LED of our generation? What monumental challenge, if solved, would change the world? Is it fusion power, promising limitless clean energy, the mind-bending world of quantum computers, or something else entirely? Now, I want to hear from you. Go down to the comments and make a case for the next great scientific quest. Don't just name it. Tell us why it matters, and why it's the next impossible mountain worth climbing. Your passion and your arguments will decide our next deep dive. The most compelling idea will become the subject of our next video. This channel is a community built on curiosity. So, if you believe in the power of science to solve the unsolvable, make sure you subscribe to Quantum Quest and turn on notifications. Thank you for watching.